Welcome, everyone. It's good to see everybody else on the line. Khalid and Robert and Calvin and Cynthia and Devin, Jason, Jay, Melissa, Robert, Twee, Titus, Vu. Thanks, everybody, for being here today. Good morning, everyone, and welcome back for a very serious topic. We're going to start talking about infinite series today. Short version, we're going to take an infinite list of numbers and we're going to add them up and we're going to see whether we get out a single number if the series converges, or if it does not reach a single number, in which case we will say that the series diverges. There's actually some cool stories that go with this particular topic, and so I think we'll get a few of them today, a few of them tomorrow. So for those of you that like historical anecdotes, I think you'll like this section. There's actually a little bit of a tie-in with music. So for those of you that are into music, you might learn something that's a little bit familiar. That could be kind of cool. I'm trying to think what else is cool. There's kind of an interesting little proof that'll come out, derivation that's pretty fun, that we'll get somewhere along the way. So there's all kinds of cool things. A little slick trick for figuring out how to represent repeating decimals. This is actually kind of, there's actually quite a bit in this section that I think you might enjoy. Good news, none of the questions here are super long or involved. Most of them are like half a page long. Probably the biggest paper issue on this particular topic is that there's a lot of dots. And so you'll end up with these long lists. And sometimes you kind of run out of paper because your lines are so long trying to figure out what patterns are. But that's probably the most difficult part of the writing in what we're doing here. But I think I'm getting a little bit ahead of myself. Very good. So today we're going to switch gears. When we were together last week, we introduced this idea of a sequence, which was an infinitely long list of numbers. And today we're going to start talking about a series. And a series is what happens when you add up that infinitely long list of numbers. For those of you that came through our Calc 3 curriculum, you would have already played with power series and Taylor series and Maclaurin series. Those would have been like infinitely long polynomials, if you will. And so this topic should be somewhat familiar. But when you were playing with the power series, Taylor series, and Maclaurin series in Calc 3, you did so without really a real understanding of what it meant for things to converge.
And that was the first time I met George Clooney.
Got him. So George Clooney signed your football cleats?
No, Danny Trejo. I mean, yeah.
No. Well, what's the difference?
Yeah, right?
That's two for...
Welcome back.
Thank you.
Oh, he's back.
This is yeah, I'm sorry, the class just took a turn in the wrong direction. The teacher came back. Craziness. Blue screen of death right in the middle of class. That was convenient.
Did you make a coffee?
Yeah, thank you. So Origin has encountered a serious problem and must close. I guess I can blame it upon my son's gaming, it looks like. Let's see. All right. Okay. Let's try that again. So, like I said, we're talking about infinite series. We're adding a whole bunch of stuff up. the first little bit's going to be some vocabulary and a little bit of notation that I hope will be familiar to you from doing Riemann sums and from working in Calculus 3. And then we'll start working on some derivations, which I hope will pull some topics together that you have seen kind of in other areas. So let me start by sharing my screen. Question about sharing the screen. Can you see the list of names that's here in the corner? And can you see my chat?
List of names, I just see the window.
No,
Oh,
no,
okay.
we just see like the document.
Can you see the whole title in this upper corner where it says Infinite Series in the upper right-hand corner?
Yes.
Oh, interesting. Because I have this list of participants and also the chat open. And there's been more than one time I moved it away because I was like, wait a second, it's showing everybody's names, and that's a little strange to have in a video that's on YouTube. But now I realize you can't see it anyway. So like it's not in the recording. So thank you for that context. All right, diving in. So an infinite series is the sum of an infinite sequence of numbers. So we got all these numbers, A1, A2, A3, AN, and then notice there's the dot, dot, dot at the end. And what are we doing? We are going to add them all up. Yay for addition. So we're adding up an infinite number of things. So the goal of this section is to understand the meaning of such a sum. You might assume that if we add up an infinite number of things that you wouldn't get a finite number, but that's not necessarily the case. So for example, here we have the number pi, and you can think about what the place value means. So you have 3.1415926, et cetera, et cetera, et cetera. And you can think about the 3 as just representing the digit 3. You can think about the 1 that follows it as being in the tenths place. So it's 1/10. And then you have 4/100ths. Here's 9 over 10 to the 5th. And so here we are adding up an infinitely long list of numbers. And what does it all add up to? In the end, it adds up to our old friend pi. This is a little bit of an odd sequence or series in the context of this class, in that there's no pattern in these numerators, the 1, 4, 1, 5, 9, that we have no formula, explicit formula that will tell us how to tell what that next digit is. We got to kind of crunch it the hard way, so to speak. But that gives you a nice introduction to what an infinite series might look like. So in general, if we want to calculate an infinite series, what we're going to do is we're going to consider partial sums. And so here in the context of this class, Sn equals the nth partial sum. Partial sum. Oh, need another bump. So S1 would S1 here means add up one term. S2 means add up two terms. S3 means add up 1, 2, 3 terms. S4 means add up 4 terms. Sn means add up n terms. And so you could write Sn as the sum from I equals 1 to n of, here you have A, I. That's A, I. Questions so far? Very good. So these partial sums form a new sequence, which may or may not have a limit. And so remember this idea of a sequence. This was the last section. So this is our last topic. So in the last topic, what we did was we talked about sequences, And what we did right here at the very beginning of section 10.3 on series is we made a connection between the sequence, which is the old concept, and the series, which is the new concept. It's not a trick, but one thing that you will have to be able to keep straight to be successful in this topic is you got to be able to keep track of the difference between a series versus a sequence. And somebody help me out. What's a nice 4-letter synonym for sequence that begins with L? Four-letter synonym for sequence that begins with the letter L.
Line?
First 2 letters are correct.
A limit?
Still the same first, but you have another letter in there that's correct. Limit has 5 letters, I think.
Oh, and math is hard.
Yeah, it is. I'm totally with you. The one I'm thinking of is list. So a sequence is just a list of numbers. And then a series, what's a series?
Sum.
It's the sum. Exactly. Thanks, Vu. Sum of the list. Okay. This isn't hard, but having taught this a whole bunch of times, I can say that just keeping the 2 of these things straight tends to be a little bit of a sticky point for many students. Questions? Ready to go on.
Series will have the sigma.
Series will have sigma, exactly. Yeah. Exactly. All right. Let's keep going. So the scan makes it a little bit difficult to read what's going on here, but what I want to point out is that here on the left we have an infinite series. So there's infinity on the top, and on the right we're saying that the infinite sum is equal to the limit as n goes to infinity of the limit from I equals 1 to n. And so this whole bit right here, right there, that's our partial sum. So that's our partial sum. And so the infinite sum, the infinite series, is equal to the limit of those partial sums. We'll see how this plays out in a moment. This should look, in some ways it looks unfamiliar because it's a new topic, but it should also look really familiar because it would remind you of Riemann sums from calculus and maybe of some of the stuff that you did in Calc 3 with power series and Maclaurin series and Taylor series. Questions about this or ready for a story?
I'm ready for a story.
Story. Yeah, we need a commercial break. We need a story. So a couple hundred years ago, there was this mathematician. You might have heard of him. His name was Carl Gauss. And he was a little guy. I think he was like 7, 8, 9. So, he was in elementary school, and he had a kind of a lazy, evil teacher. Probably wore a fur hat for all we know. But anyway, yeah, his teacher's name was, I think it was like Buettner or something like that. But what his teacher loved to do was give the students long questions to work on, and then kick back and basically watch the students suffer while the students worked. And so this one day, Buettner, the teacher, walks into class and says, all right, students, here's what we're going to do. He says, I would like you all to work through this sum. And so on the chalkboard, he asked the students to sum the numbers 1 to 100. And the way things worked at that time, they had little slates, little teeny chalkboards, and we don't have slates, but I could use paper for the sake of illustration. And so what happened was, no sooner had the teacher written this thing on the board, than little Carl comes up and he takes a slate and he puts it face down on top of the pile, or on the teacher's desk. And so the teacher's looking at the slate upside down. And then 20 minutes later, the next student comes in and puts his slate face down on top. And then the next person comes in and puts their slate face down. And so you end up with this pile of slates on the teacher's desk right in front of the teacher. And the teacher is basically was expecting to just sort of enjoy himself. But ever since Carl turned this thing in right off the bat, the teacher's been fuming inside, because the teacher was basically like, hey, there's this little brat in my class who knows that he can't get it right. And so he's not even going to try. And man, I am going to make that little pipsqueak suffer. And so in the classic style, the last student turns in his work, and the teacher starts from the top of the pile and picks up the first slate. And the first slate just says, have mercy. And pulls up the little boy that was on that one and whack, gives him a good whack on the hand, like, mercy, what are you talking about? And the next kid has his thing and he pulls it up and he's got like full of scribblings, blah blah blah, and the wrong number, and whack, and the kids go back suffering. And he works his way through the whole pile, and every single child is wrong. And finally, the teacher is pretty excited about this, because he's down to little Carl, and he pulls it up, and there's no work whatsoever on Carl. The only thing is there's just the one number, 5050, on the slate. It's the only correct answer in the class. And as the story goes, Buettner, the teacher, did the one good thing he ever did in his teaching career. He recognized that maybe he had a genius in his class, and he found him a little bit of a better teacher than himself. And so that famous story, you can Google it, and you will discover that there's many versions of the same story. Sadly, we don't have a recording of the original incident to know whether it's 100% accurate. But nevertheless, that story is how Carl Gauss was discovered. He went on to be one of the greatest mathematicians of all time. So we might say, how did little Carl come up with this result so quickly? And of course, we don't know what was going on in his mind. I mean, even if the story is true, he probably didn't remember what was going on in his mind, when he was 7, 8, 9 years old. But we might expect that Carl looked at a pattern such as this. So here we have the sum, 1 plus 2 plus 3 plus ... plus 99 plus 100. And perhaps what Carl did in his head was he took that same sum and he reversed it. And so notice we've got the original sum, we've reversed it, so we've actually doubled the total sum. And then we could add vertically. 1 plus 100 is 101. 2 plus 99, 101. 3 plus 98, 101. And all told, how many factors or how many 101s are there?
So 50.
Well, there's 1 for 1, and then there's 1 for 2, and there's 1 for 3. So how many 101s are there?
50, 100.
There should be 100 of them, right? 1, 2, 3, 99, 100 of them. And we have doubled the sum up here. So we've got to half it here, which is our 5,050. Oh, off the page again. Let me adjust the camera. Okay. This is the 5,050. We don't know what Gauss did, but this gives us an idea of how a person could do these calculations and the type of pattern someone might see that would let them add it pretty quickly. More generally, this leads to the formula 1 plus 2 plus plus n is equal to n times n plus 1 divided by 2. And so this is a sum of like a super basic arithmetic sequence. Any questions on either the story or where the formula came from? Very good. All right, so let's go back to our idea of a series. All right, so for example, if we pick up with our notes, we could ask ourselves, what's the sum of 1 plus 2 plus 3 plus 4 plus plus n plus . Now, I think you can see intuitively that this thing is adding up to infinity. I think you can see that. But I want to make sure that I make the connection with the partial sums. So what I want to point out is that we can replace this first sum, the first n items, with Sn. That's the n times n plus 1 over 2 that we just found. And so the infinite series here on the left, infinite series, is equal to the limit of the partial sums. And here's that partial sum right here. And certainly the limit of a square is going to be infinity as those terms go to infinity, as n goes to infinity. Any questions on this first example? Very good. So let's look at a second example. So here I want to add 1/2 plus a 4th plus an 8th plus a 16th. Notice these are all powers of 1/2. And so I want to start by pointing out that you're here 1/2, that would be your first partial sum. If you looked at the first 2 terms, that would be your second partial sum. If we looked at your first 3 terms, that would be your third partial sum. And so if we look at the first partial sum, we notice that we have a half. That's okay, that's fine. Don't really see a pattern yet. But if we look at the second partial sum, we notice that we have 3/4. Wait, 3/4. That's 1 minus 1/4. Second partial sum, and it's 1 minus the last term. How about S3? S3 is 7/8. Ooh, seems promising. That's 1 minus an eighth, or 1 minus the last term. And so we should be able to see, just kind of based on the pattern recognition, that the nth partial sum is going to be 1 minus whatever the last term is going to be in the sequence that we're adding. Does that make sense? Let me see if I can get a manipulate to work to show this pictorially. I had it open earlier, but it was one of the victims of my blue screen of death. So when n equals 1, the sum is a half. When n equals 2, the sum is 3/4. When n equals 3, the sum is 7/8. And you'll notice that that 7/8 is the whole one minus just one of this last little rectangle here, right? So it's 1 minus that one little rectangle. Okay. When n equals 4, n equals 4. Well, it's hard to see the shading. We added this little square when n equals 5. All that's left over is this little bit, 1/32. So it's 1 minus a 32nd. 1 minus just that one little square. That's all that's left over, which I think is 1/64, et cetera, et cetera, et cetera. Okay. And so I think it's, no. Cancel. I think that it should be clear that this overall sum, this sum right here, is equal to the limit as n goes to infinity of 1 minus 1/2 to the n. Right, that's the little size of that little chunk that's left over. And this term, 1/2 to the n, is going to 0. So this whole thing is just going to 1. Questions about this? Very good. So is the sum of any finite number of terms in this series equal to 1? Nope, not at all, because we're always a little bit short. Can we actually sum an infinite series term by term? No, because we need a limit in order to evaluate an infinite series. At the same time, we can determine the sum by defining it to be the limit of the sequence of partial sums, which in this case is 1. So our knowledge of sequences and limits enables us to break away from the confines of finite limits. Like, we now have the freedom to work with infinity, which is a beautiful, wonderful thing. So the next page is basically a little bit redundant. So it's just giving us some of those definitions. So if you have a sum with an n in the upper limit, then we would say this thing is a partial sum. What we're going to really care about is whether the limit of those partial sums goes to a number. If it goes to a number, then we say that it's convergent. If it doesn't go to a number, then we would call it divergent. I think we talked a little bit about that yesterday or last week. So you have convergent and divergent series. Furthermore, once we have a convergent series, we can use the following theorem to combine and or decompose series. All of these statements should be familiar. So notice that the constant on the inside can come outside of the summation. Notice you can have a sum of sums, and you could split it up. Same thing for differences. The thing you got to be a little bit careful is that this is only true for convergent series, and so you just it's kind of this irony that in order for this to work, you need to have convergent series, but oftentimes you won't know if you have convergent series unless you try it. So it's almost like you try it, you see whether it works, and if it works great, you keep going. Questions about any of these definitions or theorems? Very good.
Dusty,
Mm-hmm.
do I see right in the last page where it works for addition but not subtraction in the quantity?
Down here?
Yeah, I see that number 2. It says, oh, I'm sorry. I thought it said did not equals. Never mind.
Yeah, no, it works in both cases.
Gotcha.
Yep. Yeah. And basically what these theorems tell you is that the stuff you want to be true is true. Like, it's not always going to be the case, but at least for scalar multiplication, addition, and subtraction, your intuition holds, which is nice, provided you have convergent series. Okay. Here is the next important thing that we've got to mess around with. So we're going to work with the geometric series, and we need to find a formula to represent the sum of an infinite geometric series. In this case, this is it's not hard, but it's kind of important. So A is equal to your first term, and then R is your common ratio. And I think we talked about those back when we were talking about sequences. So what happens if you add a whole bunch of these fellas up? Okay, this is an important formula, and I think it's worth spending a little bit of time and deriving the formula. So let me make sure you understand what we're going to do. So we want to find the sum of an infinite geometric series, but in order to find the sum of an infinite geometric series, we're going to start by finding a finite sum, i.e. the sum of the partial sums, and then we'll look at a limit as n goes to infinity to find the infinite sum. Let me work through this one by hand. All right, so here's your geometric series. It's a series because we're adding all the terms together. It's geometric because you have this first term, and then each time you're multiplying by a common ratio. Question for you, how many terms are on this list? How many things am I adding up on this list?
Infinite.
And
It's not infinite. There's no dot dot dot
N
at
minus
the end.
one.
N minus
N
one.
amount of times?
That we're adding n items,
and time.
right? And you see the power of n minus one, so that's like a little bit of a bait for you. But notice that very first A doesn't have any r's in it, so it's r to the 0, r to the 1, r to the 2, all the way up to r to the n minus 1. We started at 0, so there's n terms here. So to find this sum, what we're going to do is we're going to multiply the whole thing by 1. Is everyone satisfied that if I multiply by 1, that it won't change the overall sum? It's like one of the
Okay.
oldest algebra tricks is you multiply by a special one. So a plus a to the r plus a to the r squared plus dot 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 plus a to the r, a r to the n minus 1. And then I'm going to multiply by 1 minus r over 1 minus r. Okay. Everyone see that the pink stuff is just 1? Okay, so now I got to be a little bit clever. I'm going to distribute, and maybe to keep things straight, maybe I can distribute the 1 first. So if I distribute this is going to be too big for the page, just FYI. So if I distribute the 1 first, I'm going to have 1 times a, which is a, plus 1 times ar, ar. You can see pretty fast what's happening. I'm getting back the same thing. That we started with. That's what happens when I multiply the 1 by all that stuff. Then I can come through and I can multiply, I don't know if the orange shows real well, I can multiply the r by all this garbage. So I can have a times negative r. So a times negative r, which would be negative ar. Ar times negative r minus ar squared. You can see all these are going to be minuses. The term immediately before this one, before ar to the n minus 1, would be ar to the n minus 2 times r would be ar to the n minus 1 minus the very last term would be ar to the n. All this stuff is divided by 1 minus r. Good news. Plus ar minus ar. Plus ar squared minus ar squared. Plus ar to the n minus 1 minus ar to the n minus 1. Leaving us with just a minus a times r to the n minus, sorry, a r to the n over 1 minus r. If we factored out the a, that would be a times 1 minus r to the n.
Oh, I think he crashed again.
No, I'm still here.
Oh, he's back.
I'm back, sort of.
Okay.
Questions
It
about
worked
this?
out.
Questions about this result?
Nah.
Very good. So let's see, what does that mean? This is the partial sum. And so if we want to find the infinite sum, what we need to do is we need to let n go to infinity. And so when we let n go to infinity, we can look at the limit as n goes to infinity of Sn, which would be the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. Let's try out a couple values. So if r was equal to 2, for example, what would happen to this limit? If r was equal to 2, what's going to happen to 2 to the n?
It's gonna convert. No, should diverge.
It's going to diverge because it's going to go 2, 4, 8, 16.
Infinite.
It's going to go to infinity, right? If r was equal to 2. If r was equal to -1, so if r was equal to -1, we would have like -1 to the 1th. So you go -1 plus 1, -1 plus 1, -1 plus 1. And so it would be bouncing back and forth, right? And so this term would diverge. It's not going to infinity, but it's bouncing back and forth. If r was equal to 1/2, what would happen?
It gets
Converge.
smaller and smaller. So it would hit a number.
Yeah, so if r was equal to 1/2, the 1/2 to the n would approach 0. And so this part would go away and you'd be left with just a over 1 minus 1/2. Let's see if we can pull that back together. So we go through our long derivation, and what we find at the end of our long derivation is that the infinite sum, notice you have infinity in that upper bound, of a times r to the n. Yeah, here I've started it at 0 is the way I've written it, is equal to the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. We just did all this part. And this is going to converge to a over 1 minus r for r's between -1 and 1, and it's going to diverge elsewhere. Let me do this on a number line for you. So here's 1, here's -1. What we're saying is that in this region, it's going to converge to a over 1 minus r. But on the outsides, both directions, it's going to diverge. It's not magical, it's just the limit of the sums. As we're trying to wrap it up, I just want to make a kind of a cool side note. For those of you that are maybe have borrowed money to buy a car or have a house loan or any type of loan, this formula right here is the mathematical basis of the loan amortization formula. So that derivation we did is the same one you do if you wanted to try to figure out your house payments, for example, your car payment. That's kind of the bad side of this formula. The good side of it is this is the same formula that you would use if you were saving for retirement. And so if you wanted to put $5,000 a year into your Roth IRA and figure out what happened, this is the same formula that you would use to figure out how much you'd have by the time you retire. So this geometric sum can work for you if you're saving your money, but it can work against you if you are it can work against you if you're borrowing money. So kind of a cool connection. And I think there's one homework question that is about that. So kind of the sum, or to sum it all up, I guess pun intended, here's our geometric series formula. And this is the first of a number of formulas that it's worth tracking in this class. And we'll make a big deal of this tomorrow. It's not difficult. Geometric series aren't difficult to recognize or difficult to work with, which is why we begin with them. But they are really nice because they're clean and, relatively speaking, easy to understand. So as we conclude today's lesson, may all this series stuff make sense to you. May you enjoy kind of the puzzle and the connection and the historical anecdotes that go with it. But also, may you all be blessed with computers that stay working and internet that stays consistent in a world when we are very much dependent upon these kinds of tools and toys. Have a wonderful day, everyone. I look forward to continuing this topic with all of you tomorrow. And that concludes today's lesson. Take care.